Mr. Doolin. I thank you so much for tuning in. So today what we're going to do is we're going to take a look at ideal gases and the ideal gas law. So we're going to define what ideal gases are, right? Why most gases behave under certain conditions as ideal gases, why some don't, and then we're going to define quantitatively how do we deal with gases when we are at non-standard conditions, non-STP, non-standard temperature and pressure conditions. So I guess let me start out by saying normal conditions like standard temperature and pressure, and I'm going to go ahead and abbreviate it as STP. You need to understand that means standard temperature and pressure. Most gases behave qualitatively like an ideal gas. Now, the definition that you'll be looking for an ideal gas is essentially like what we've been talking about in class up till now, where we've got these pressure to volume relationships, kinetic molecular theory, right? And the predictive power of us being to say, okay, if I decrease the volume, I'm going to increase the pressure, and this is why, right? That is ideal gas behavior. Remember, kinetic molecular theory, we had our assumptions that we were making, and those assumptions were essentially giving us the assumptions needed to make them ideal gases, okay? So a lot of our gases, like our nitrogen, oxygen, hydrogen, noble gases, carbon monoxide, carbon dioxide, so all these different types of gases, at standard temperature and pressure, they will actually behave like normal, ideal gases. Now, before we move on and I forget, I do want to go ahead and define what the values of STP are. So the values that we will be working with is actually 1 atm of pressure and 273 Kelvin, right? So this is my standard pressure and this is my standard temperature. So as long as I'm at those two conditions, my gases will behave as ideal. And then just to give you a heads up, under these conditions, our relationship 1 mole equals 22.4 liters is true. So what we need to do is 1 mole equals 22.4 liters at STP. So we need to adjust that. All right? And so generally, as gases behave more like ideal gases, the higher the temperature, right, and the lower the pressure. So ideal gases are more ideal, if you will, at high temperatures and low pressures. And this should make sense to you. At high temperatures, I've got my gases moving so fast, right? I've got them so far apart that they essentially really don't interact with each other, all right? And then also at low pressure, we've got less collisions occurring, and so I don't have to worry about energy lost or gained during those assumed to be elastic collisions, all right? And so most gases behave more ideally the higher the temperature gets and the lower the pressure gets, all right? Okay, so now we have to really look at what is an ideal gas? How are we going to define an ideal gas? Well, an ideal gas actually has a constant pressure volume value. And so remember, we talked about this in the last lecture. We would say that pressure volume is a constant. There we go. Remember how to spell. And so what this does is this tells me that a gas is ideal. If I change conditions and I'm going to stay close to whatever this constant value is, then I know that I'm dealing with conditions that allow me to assume that this gas is an ideal gas. All right? So when we look at this, I'm going to create a graph here. Okay, and so what I've got, and take a minute to go ahead and sketch this graph. Now, don't miss this yellow line as it goes very linearly straight across the graph here. So I've got my pressure volume on my y-axis. That's liters.atm. And then I've got my pressure down here. I guess the units of that would be atm. And so as I adjust the pressure, what I would assume is that this PV value would remain constant. Well, this is what we actually see. If I'm looking at, say, neon, which is a noble gas, neon actually doesn't hold true to this or I guess not completely. It's pretty close, so notice I don't get a whole lot of variation. If I'm going to look at oxygen, I'm going to see the same thing. Oxygen is going to vary just a little bit, right, from that constant PV value. And so again, qualitatively, this is why if we get closer to those STP values, those low pressure, high temperature values, we'll get closer and closer to that ideal constant PV value. But what we see, and this is where it starts to get a little bit tricky, is we see carbon dioxide does this. So carbon dioxide doesn't follow that constant PV value very well, especially as the pressure is increased. We notice as we increase pressure, we get further and further away from those ideal qualitative conditions, right? And so why? Why does CO2 deviate from that ideal behavior the most? All right? And it has to do with the molecular structure of carbon dioxide. Carbon dioxide is a heavier molecule. It has more electrons, right? And so what we see is that in carbon dioxide systems or in carbon dioxide samples, we have more London dispersion forces, which are our intermolecular forces between molecules. And so our London dispersion forces are higher than we see in neon and oxygen. And so my gases interact more, right? So then it becomes perfectly clear that, well, those collisions are not completely elastic. The gases do interact with each other in real life, and the further we get away from those ideal conditions, the less ideal my gas becomes. And so now we have to really ask that question. What should that PV value be under ideal conditions? Because the truth be told, ladies and gentlemen, the further I get away from STP conditions, the less I can actually use predictive powers, right? So no fear, what we end up with having to do is we have to end up using the ideal gas law. So this is your ideal gas law. And we've introduced it in that KMT section. And so see here we've got our pressure volume relationship to our nRT. Well, this R value is known as the ideal gas law constant. The one value that I am going to want you to memorize is 0.0821. The units on that are liters times ATM, Kelvin times mole. And so those are my units. Now, the R values, they do have different values. Notice our pressure is in ATM, and it lines up with the pressure in the particular R value that I want you to memorize. And so if you're going to use the ideal gas law in these particular situations, you're going to want to make sure all your pressures are in ATM if we're using this particular R value. If you don't want to do those pressure conversions, ladies and gentlemen, there is going to be a formula chart that's got all the other R values on there that you may use. All right? That's going to be your choice that you can do that or not do that. All right? So the question becomes, as I move away from my ideal conditions, how do I start to calculate, say, the number of moles, or calculate the temperature, or calculate the volume, or calculate the pressure? And so what we do is we use the ideal gas law to correct back to what that particular pressure value would be under the conditions that are not ideal. And so the big thing that I'm going to leave you with here, ladies and gentlemen, if you are dealing with a gas at non-standard conditions, you will need to use PivNert to calculate those pressure, volume, moles, and temperature values. And so write that really big across your page, ladies and gentlemen, because this is so important for you to understand. If I have gases at non-standard conditions, I will have to use the ideal gas law, right, to correct under those conditions and be able to calculate the pressure, the volumes, the moles, and the temperature. All right? And so at this point, it really does just become an algebra problem because you'll normally be given 3 out of those 4 variables. And remember, R is always a constant. We'll always know what that is. And just in case some people are wondering, what the heck is this R value? You can think of it as the correction factor. It corrects those values back to what the gas would look like under ideal conditions. All right? Okay. All right, so ladies and gentlemen, hopefully you got that very last statement. Again, gases, non-standard conditions. We've got to use PivNert if we're trying to convert from one to the other. The other thing that I will tell you, notice in the first couple of lectures we were changing one variable to another. Like, hey, I was going to increase, go from pressure 1 to pressure 2, like increase pressure. And I was going to say, hey, if my original volume was this, what's going to happen to my volume? So notice on those we're changing one variable and predicting what's going to happen to another. In this one, I'm not changing anything. I'm saying, hey, under these conditions, at this snapshot in time, what do these values look like? All right, and so that's another really big thing for you to get into your head, ladies and gentlemen. PIVNER, the ideal gas law, gives us a snapshot of what those values are for those gases under the conditions that are given. And again, we use them for gases that are under non-standard conditions. I hope you get that into your head. Okay? All right, so if you got questions, get them down. I'll see you in tutorials for those. And otherwise, I will see you in class.